Hey everyone, welcome to this explainer. I'm absolutely thrilled you're here today. We're going to unpack something that honestly is just truly fascinating. Have you ever stood at a port, looked out at one of those massive, towering steel cargo ships stacked literally hundreds of feet high, and just wondered, how on earth does that mammoth structure not just sink straight to the bottom, especially in the middle of a raging ocean storm? Well, today we're exploring the brilliant mechanics of ship stability. We're going to decode the invisible physics that govern exactly how these giant ships stay upright in rough waters. It's a fantastic topic, so let's jump right in. Okay, let's dive into this. Here's our quick roadmap for today. We're covering 1. How heavy ships float. 2. Gravity versus buoyancy. 3. The Metacenter explained. 4. 3 types of equilibrium. And 5. The angle of Loll. By the end of this explainer, I promise you're going to look at every vessel on the water in a completely different way. So starting with part 1, how heavy ships float, the core paradox. When you think about the sheer scale and that overwhelming weight of modern vessels, we're talking hundreds of thousands of tons of pure metal. The math just seems completely wrong at first glance. It really boils down to this almost childlike but deeply profound question: how does a giant steel ship actually float? We know the fundamental law of flotation, right? A solid body floats in a fluid if the mass density of the body is less than that of the fluid. That's exactly why wood, plastic, or ice cubes float. But steel? Yeah, that's a whole different story. Let's just compare the numbers for a second. Freshwater has a density of roughly 1,000 kilograms per cubic meter. Saltwater is slightly higher. But the mass density of the steel used to build a ship, it sits at approximately 7,850. That means it's nearly 7 times denser than water. It's basically a giant anvil. So based strictly on material density, that ship should literally plummet to the ocean floor immediately. So what's the secret here? Well, the mystery is solved by Archimedes' Principle. Simply put, an object submerged in a fluid is subjected to an upward buoyant force that is exactly equal to the weight of the fluid it displaces. Because the ship displaces a massive amount of water and its hull is mostly full of low-density air, the overall average density becomes less than the water, and that is what allows it to float. Moving right along to part 2, gravity versus buoyancy, the invisible tug-of-war. Now that we know why the ship is actually sitting on top of the water instead of at the bottom, we really need to look at the continuous, invisible physical battle happening right beneath the surface, even when the ship is just sitting perfectly still in calm waters. Let me introduce you to the 2 main characters of our story. First up, we've got the gravitational force, represented by the letter G. This is the vertical, downward weight of the entire ship, acting right through its center of gravity. Opposing it is the buoyancy force, represented by B. This is the upward vertical force equal to the weight of the displaced water, acting up through the center of buoyancy. I want you to think of them as 2 perfectly matched opponents locked in a delicate, never-ending tug-of-war. For a ship to remain completely stable and in perfect equilibrium, these 2 forces absolutely must be exactly equal and act in opposite directions. The center of gravity and the center of buoyancy should line up perfectly on the exact same vertical line. The center line. Gravity pulls straight down, buoyancy pushes straight up, and boom, they perfectly cancel each other out. But out on the ocean, the world is rarely perfect, and those waters are rarely calm. This brings us to part 3, the Metacenter explained, when things get rough. Now, what's really interesting here is what happens when the wind howls and the waves crash into the side of our perfectly balanced ship. Let's walk through this brilliant action and reaction sequence. Step 1. An external force, like a big wave, tilts or heels the ship over to one side. Now, assuming the cargo inside hasn't shifted around, the center of gravity stays exactly where it was. But look at step 2. Because the ship is tilted, the volume of water displaced on the low side is suddenly much, much larger. This causes the center of buoyancy to physically shift over to the low side, to a brand new point we call B1. And because gravity is pulling down in one spot, and buoyancy is now pushing up from a totally new offset spot, step 3 kicks in. A horizontal gap between these forces opens up. This creates what naval architects call a righting lever, or a righting moment, which actively works to twist that ship right back to its upright position. Now, this physical shifting creates a brand new, highly critical geometry point. If you draw a vertical line straight up from that new center of buoyancy, B1, and see exactly where it intersects the ship's original upright center line, you find the transverse metacenter, represented by the letter M. And make no mistake, locating this exact point of intersection is arguably the absolute most important task in naval engineering. Why is it so absolutely crucial? Because of the Metacentric Height, or GM. This is simply the vertical distance from the center of gravity, g, to the metacenter, m. I really cannot overstate this enough. This single measurement, the GM, is the ultimate deciding factor in a ship's stability. It literally dictates whether a ship will survive a massive storm or roll completely over. And that leads us perfectly into Section 4, 3 types of equilibrium: stable, unstable, neutral. Depending on the length and the direction of that metacentric height we just talked about, a ship is going to find itself in one of 3 highly dramatic states of equilibrium. Here's a super quick overview of the 3 states. We have stable equilibrium, which is characterized by a positive GM. We have unstable equilibrium, which results from a negative GM. And we have neutral equilibrium, where there's essentially zero restoring moment acting on the vessel. Let's break down exactly what these mean for a ship that's actively fighting the waves. Let's contrast those 2 primary states. In stable equilibrium, the metacenter, M, is located above the center of gravity, G. This gives us a positive GM, so when a wave hits, that righting lever we talked about earlier works to push the ship back upright. It naturally wants to fix itself. But in unstable equilibrium, it's the exact opposite. The center of gravity, G, is located above the metacenter, M. This means the GM is negative, and in this terrifying scenario, the forces don't create a righting lever, they create a capsizing lever. Instead of pushing the ship back to vertical, the buoyancy and gravity actually team up to force the ship to heel even further over. Now you might be thinking, okay, a negative GM means the ship instantly flips over and sinks, right? Well, actually, here's a totally fascinating twist. A small negative GM doesn't always mean an immediate capsize. Sometimes, the ship somehow manages to catch itself before it's completely too late. But how on earth does it do that? That brings us to our final part, Section 5, the angle of Loll, a strange resting place. This introduces one of the most eerie and honestly fascinating physics concepts out on the water. Imagine our unstable ship tilting further and further over because of that capsizing lever. As it tilts, the shape of the hull pushes deeper into the water on one side, meaning the center of buoyancy keeps moving further outward. Eventually, if the ship is really lucky, it reaches neutral equilibrium. This is the exact, highly precarious point where that outward shifting buoyant force finally lines up perfectly underneath the center of gravity once again. Because they're vertically aligned once more, that capsizing moment just disappears. The ship literally stops rolling mid-capsize. And this brilliantly illustrates the angle of Loll. The angle at which this struggling ship comes to a halt is called the angle of Loll. It's the specific angle where a vessel with a negative GM comes to rest in still water. It hasn't flipped entirely, which is good, but it's now trapped at this permanent, really awkward, and highly dangerous tilt. What's truly frightening about this state is that the ship has basically established a new normal. If a wave hits the ship now, it's going to oscillate and rock around the angle of Loll, not the safe, upright, vertical position. Its whole baseline is just permanently skewed. Let's look closer at the dynamic of this oscillation. If a wave pushes the ship to tilt beyond its angle of Loll, the center of buoyancy moves even further low. This finally creates a positive righting lever. But here's the catch. This righting lever doesn't push the ship all the way upright. It only has enough mechanical geometry to push the ship back to the angle of Loll. If the wind blows hard from the other direction, the ship might aggressively flop all the way over to the exact same angle of Loll on the opposite side, port or starboard. And if that center of buoyancy fails to move far enough out to catch the gravity line, the ship will inevitably capsize. This is exactly why a negative GM is an absolute nightmare scenario for any captain. So we can pretty much distill all of this complex naval architecture and physics down to one ultimate golden rule, drawn straight from our sources. Always keep the ship's center of gravity below the metacenter to be in stable condition. Heavy cargo goes low down in the hull, keeping G down, ensuring a strong, positive metacentric height, and guaranteeing that when the ocean tries to knock the vessel down, the ship's own geometry fights back to stand it firmly upright. I really hope this explainer has shed some incredible light on the invisible forces battling it out right beneath the waves. So the crucial point is this. The next time you see a massive vessel conquering the ocean, you won't just see a piece of metal floating. You're going to see a perfectly engineered balance of gravity and buoyancy, righting levers, and shifting metacenters. I want to leave you with this final, provocative thought to ponder today. In whatever you are building or balancing in your own work, is your center of gravity safely below your metacenter? Thank you so much for joining me today, and keep exploring the amazing mechanics of our world.